This meeting is being recorded.
Hi, good afternoon, everyone, and welcome to quantum computing. Today we will start with Horst Kuhnhardt's part on quantum computers and programming. He'll provide some insights on this to you, and after this, I will say more about the seminar presentation. So, Horst, the floor is yours.
So thank you, Patrick, and hi from my side. Good afternoon. We started already with the more hardware view on quantum computing and the various applications or architectures that quantum computers are nowadays built. And from that perspective, I want to start this afternoon lecture after I hand over to Patrick in roughly an hour. So what do we plan today? I want to wrap up a bit from that where we met last time in our lecture. And please let me share my screen. I've prepared some slides to introduce you in the programming software development kit we use, or I can recommend, I have to say, IBM Qiskit software development kit, because it's easy to handle and there are a lot of tutorials you can use for that. So Patrick, do I have the right to share my slides?
Yes.
I'm not sure.
Everyone can screen share.
Get a message that it is blocked.
Okay. I can try to quickly do a screen share on my side and see if this works. So you should be seeing.
Yeah, I see your slides.
Maybe you can try again.
No, I'm not allowed to share my screen.
Because the setting says that you
a message. So sorry for the delay, dear students. I want to wrap up a bit on the quantum computer technology, and there are some approaches in Germany and in the European Union to build up a kind of ecosystem, a quantum computer ecosystem that is managed in Germany by the German Aerospace Center, DLR, located at Jülich and other places in Germany, like in Hamburg or like in Ulm. And I want to share you some information and a new published book. It's open access and it deals with quantum software, how to develop secure and reliable and efficient quantum computer software. This book is available as open access. That means for free. You can download the book, and I could recommend that literature for you. But first, let's have a look at our quantum computer ecosystem. To repeat some of the information that I gave you in my first lecture in this module. We have various forms of quantum computer hardware or architecture. There are some competing approaches. The company D-Wave in Canada follows more or less the quantum annealer approach. Some say it's not a real quantum computer. It has something to do with annealing. It is more a technology that is used in thermodynamics or in industry as well, in chemistry. But the company D-Wave is very successful with that quantum annealer approach, and some problems, mathematical problems like optimization problems or simulations can be very good handled with quantum annealing technology. I would say the real approach in quantum computer hardware or architecture are ion traps or NMR systems or atoms on an atomic way or photonic chips. Though there are a lot of approaches that are competing today with the first real world implementation of a quantum computer. And I think that's important that especially we in Germany or in the European Union are at the beginning of the development of a quantum computer ecosystem. That ecosystem has been built up by international companies like IBM, and therefore I want to share with you some information on the IBM quantum computer ecosystem or Hitachi or Google or others. So it is a competition right now going on. And to give you some insight in the German initiatives, I want to switch and share a new screen directly to the website on quantum computer ecosystem. So here we are. There is a German and an English version of this website. And here you can find the latest information on quantum computer simulators and the innovation centers located in Hamburg, Innovation Center at Ulm, and a list of projects that all deal with quantum computing. So it is a ministerial funded organization or project, this quantum computer ecosystem by our German Ministry of Economics and Climate. And the aim of this project is to bring the industry and the research projects together to develop a system where we can exchange best practices in the development of real-world quantum computers. And right now, they are working on a 4-qubit demo version or 4-qubit version, very a few qubits in a hardware-based system. And therefore, you can search some or to research some project on working on organic molecules for quantum computing or diamond material. Please remember the architectural approach with diamonds as a basis, then neural atoms quantum computing, then prototype on an ion trap. That was one of the first implementations of quantum computer hardware, and photon-based, if you want, light-based integrated quantum processors. And here is one machine from QC, a demonstrator on a 10-qubit ion trap version. So there are some projects right now in the quantum computer world, especially funded by the German government. And we have also a European flagship program in developing quantum computer hardware, quantum computer ecosystems in the European Union, because our competitors are international. Of course, China, of course, the US, and other countries working in the field of quantum computing. And here you can inform yourself a bit on these quantum computer systems that we have already available in Germany. In the other fields, this book I already mentioned for you. You can find under services, publications, some newsletters or this book on quantum computer software. It is for free. That book handles aspects on theory and system design. So some additional reading or further reading according to our lecture from Patrick and me on this field of quantum computing. We have some events that are coming soon in this field. Showcase in Hamburg, 18th of November, and some services, career option in the field of quantum computing. And I think it's a good thing if you make yourself a bit familiar with this future or outstanding technology on quantum computing. And in this landing page from the German quantum computer ecosystem, you can inform yourself on the system. Yeah, but today we want to say a couple of words, or I want to say a couple of words of the quantum computer platform offered by IBM. That's one of the platforms you can work with in order to develop your first quantum computer software projects. And of course, you always need a specific quantum computer hardware or a simulator on a general purpose computer that simulates quantum processes, quantum gates. But I think it would be more interesting for our purposes that you can work with software, first software developments on a specific quantum computer offered by IBM. That is located next to Stuttgart in the western part of Germany. Ehingen and IBM built up the first German quantum computing center, if you want, directly at this place at Ehingen. So the connection from your browser or from your client directly to the quantum computer hardware offered by IBM or others is in a cloud-based technology. And you have to apply or have to build up an own account on this quantum computer platform. So here is the starting point. You have to make an account. It's free of cost. You have to only share your web address, then type in a password. Then you get immediately an access via a shared code directly on a separate way, on a second way via your smartphone or via your email system. And then you have approach to the IBM quantum computer platform. The platform handles or gives you an overview on a dashboard. In the dashboard, you can see information what's going on right now on the quantum computer at IBM. How many projects or how many computations have been done recently or actual. Then what are the resources that are offered here? And you see some quantum computer systems, 156. That's one of the biggest implementation of IBM in the field of quantum computing, and some smaller ones. You can see the workload of these systems. And here are what we can combine or compare with the CPU approach, the central computing processing units. IBM calls that quantum processing unit a QPU. And you can also watch the workloads on the specific systems, how many processes are completed or what's going on right now. So going back a bit to the quantum computer platform And I want to give you some information. What are the necessary steps? How could you develop your first quantum computer software? And Patrick and me, we recommend that you try, that you find out how could your first quantum computer program look like, and what is an algorithm you can work on with this platform. And the dashboard gives you some information on the shared documents. So what we have now available are three instance QPUs that are available right now, and all QPUs offered by IBM for this test environment or testing environment are at all are 11 QPUs at all. I would recommend that you make yourself familiar with all the really excellent learning material offered here at this landing page. So it is Quantum Computing in Practice, or explore all the courses and tutorials. There are really a lot of information offered here. And you have access to all that information. So there are the information on the basics of quantum computing, and we try to give you a first summary of first information on this technology, on this new technology, based on entanglement, based on quantum gates and various hardware approaches in that field, and some fundamentals on quantum algorithms, and some general information, as well as a kind of outlook. How could business foundations or an ecosystem look like in the field of quantum computing? Quantum computing are always in the same context with quantum safe cryptography or post-quantum cryptography. What is needed for an encrypting algorithm to be safe in the quantum world. And therefore, I think it's very interesting to handle that topic on quantum cryptography and quantum safe cryptography. Maybe you decide in your seminar work to handle one of that problems or topics in that. So going back a bit to our dashboard. So the dashboard is always the communication platform or the landing page for the IBM quantum platform. And I want to step in the first quantum program. As it is in most other programming languages, it is more or less the Hello World topic, the Hello World program that is available in all the programming language or programming lectures. So IBM delivers a lot of videos, a lot of tutorials in that field, and I want to go with you through that first overview, how you can make yourself familiar with that system. And in that first quantum approach, there are two parts followed. A simple quantum program based on quantum gates and on a real quantum processing unit, and the other ones are more simulation programs. You can do both. So Qiskit is the name of the programming language or the software development kit IBM has developed for programmers or for beginners or for students. And I don't want to go in every video. I leave it to you. I leave it up to you. But the videos use more or less a runtime service that is offered by this quantum computer platform. So before you begin, you have to do some preparations with your system. There is a Jupyter notebook available where you can do most of the programs, and that what we recommend with the experience of our last lectures in that module, quantum computing, that most of the students work with Jupyter notebooks. And we shared in the seminar presentations the Jupyter notebooks. So that's part of the seminar work you have to do. But Patrick will inform you on that later on. And we always have to do some visualization with the results that we found in the application of the software. And here again, it is a structured approach, how you can work easily with that platform. And I would recommend that you visit the Basic of Quantum Information course. I already showed you where you can find out the videos, the tutorials in that field. And it's a step-by-step process. And start from the beginning. You are guided through these lines of videos and slides and information. It is more or less further information from that what we gave you and what we prepared you in the slides in our materials for this course. So you can download slides and use that information in order to prepare your materials for the seminar paper or for your own information. So what are the steps to create and run your first simple quantum program? So of course, like in other programming programs or programming languages, you first have to map the program and you should code it in a quantum native format. What is a quantum native format? More or less, you have to find out what are the quantum gates, like the Hadamard or the DHZ format that is used in the programs. Then kind of optimization of the circuits and the operators you use. Then the execution using quantum primitive functions. Primitive functions from other programming languages can be compared with that. And then starting the transpiler. Maybe you know the term compiler. Compiler is more or less used to transform a code in a programming language like C#, Python, Java, or whatever, in a machine language code. And the transpiler is doing similar task. The transpiler converts a source code from one language into another language. And the language a quantum computer understands right now is based on this quantum native format. So it is called a transpiler. So let's go a bit through these various steps. So how could you map the problem to a quantum native format? So there are some tools that you can use. And maybe to repeat some terms on basic computer science, IBM uses the least significant bit ordering numbering system. Maybe you know that from the first lectures in computer science. If not, please look it up. We have several methods, or you will find several methods in how the bit ordering system is used. We have a least significant 0-bit numbering scheme that is used from Microsoft. So, and here is one of the first software programs using Qiskit. It is compared, it can be compared to other programming languages that C, C# or other languages. You always have to kind of include a session where you import from a library quantum circuit and import the operators and a preset path manager and so on. And on that basis, you can build up your first steps in that field. So as I already said, quantum programming or quantum code is working on circuits, and there are a lot of quantum circuits or quantum gates that is offered in the software development kit. And with that system, we could create, for instance, an Hadamard gate with a qubit 0 initialization, and it is simply the code QC quantum circuit dot H initialized with 0. That's a Hadamard gate, and performed a controlled X gate on qubit number 1, controlled by qubit number 0. That means we have created with these few lines 2 qubits with a Hadamard gate, and the return of that simple code can be showed in this description or in this image here. So you can inform yourself on Qiskit primitives. They are explained directly under the following link. I don't want to go directly in these details because that information is shared with Patrick's part in detail, so I don't want to build up redundancies in our lectures. So the sample, I think you know, in quantum computing, we have to do a lot of measurements. There is not only a run once and result is immediately available. In some quantum computer implementations, you have to repeat some runs, some run over programs 10 times, 100 times, 1,000 times. This is the question of measurement. And the more measurement, as more exact is your solution. And here are some code examples on 2-qubit Pauli operators, but all the information is in the slides from Patrick. So if you have made up your minds on the problem, on the algorithm, of course, we have, or you have to optimize the circuits and the operators. So the transpilers or the quantum computing environment is not as comfortable right now as other compilers like optimizing compilers like C compilers or whatever. But there is a development still going on, and the basis of all that elements is always an instruction set architecture, ISA abbreviated. That is something like the machine code of a quantum processor. And here are some examples, code that starts some real devices to submit a job. And maybe you know from other programming languages, we speak of a job or a batch job or a runtime application in this programming environment. And with these few numbers, you create a global phase of various gates, and these gates can be processed by a back end, and the back end is, in our imagination, the quantum computer or quantum processor unit. Let it be an ion trap, let it be atomic, or let it be a photonic computer. That is something what the implementation is all about. That should be hidden or be transparent from the programming language. But right now, quantum computer programming, I compare it a bit with the first steps in programming, that the high-level programming language hides more of the details of the underlying machine, as it is in high-level languages like Python or like other languages, C# or Lisp or whatever. And in the beginning, or the first steps should always be a machine-oriented programming language like an assembler code or whatever. But in most of the cases, we need only a knowledge of this machine language or instruction set by a specific machine in order to do an optimization in the form of the runtime or in the form of a space requirement, memory requirement, or to speed up an algorithm. But right now we are not so far in this step of quantum computing. So a next step in the development is always the execution of quantum primitives. So quantum computers can produce more or less random results because it's depending on superposition, on the entanglement on the systems, and to collect a sample of outputs. And these primitives are listed here or summarized here, where you can produce an output in that form what a specific job is producing. So after this job is submitted to the environment, to the quantum computing environment, the job is completed like on every other machine with your current Python instance. And this is the form of a job, and the job can be transferred to a machine, and it is handled by the machine and calculated by the machine. In our case, it is the quantum computing environment, and the result can be visualized or can be visible by two ways in order to do a measurement in the specific hardware of a quantum computing or using a simulator. So the recommendation is that you use both ways. In the first way, to use the quantum computer hardware and to combine the results or to compare the results using the simulator. It's called the Qiskit runtime local testing mode, where you can test your algorithms. Then you will get to see some results to be analyzed, and it could see that you have some measurement, some errors in the measurement, and that is very often in the quantum computing world that you have to do a lot of measurements in order to find out the precise element, and therefore the system must work under specific environmental conditions like the zero noise environment. You should not have any temperature differences or problems in the field of environment where the system is placed in the specific hardware quantum computing center. So a sampler that could so that's the form of results that you will see. So you have the values and a specific set of observables where you can find out your values of the specific algorithms, and the qubits here we have used 2 qubits, the independent expectations of the values of the x and the z axis. So the scaling process to a larger number of qubits is a process of optimization. So if your quantum computer algorithm you want to apply to a 100 qubit GHZ state, and GHZ stands for Greenberger Horn-Seilinger entangled quantum state. So that's a specific state of a quantum computer, and this environment offers you a range from 100 qubits to with over 1,000 gates. So that's a big opportunity for that. But we are, in our case, where we use it as a testing platform, a bit limited. So IBM, sorry, offers some premium access to a more qubit version. So again, following the same steps that we already learned. The first step is mapping the program. I want to go a bit through it and show you the results. So create the first quantum circuits and apply with the operators your values into the system. And after the execution on the specific hardware, you will find out and see the results. And here again, there is a lot of measurements available necessary in this 100 qubit GHZ state system, where you have a lot of measurements of the correct results. So going back a bit to the first step, to the programs. So you have kind of a tree-based system where you find out on the left-hand side the development workflow of your first software and the introduction of the Qiskit pattern. So Qiskit as a specific programming and open source available software development kit. A lot of information is shared on GitHub, and I'm convinced you will find a lot of information to do your first quantum computer programs. Then again, mapping of the program up to the circuits. Then the optimization process to the specific hardware you are applying the code. Then the execution and the post-process check of the results. Interestingly, you find out some, you could use maybe also an assistant in the field. There is development support and a Qiskit code assistant that's based on artificial intelligence. And I think that's one of the reasons because companies like IBM or Google or whatever are offering their development platforms, because with every project that is handled on that platform, the company builds up a kind of knowledge base on available on algorithms, on projects, and builds up a knowledge base for that field. And therefore, artificial intelligence comes into the game because these products like the code assist, the Qiskit code assistant can the code assistant has been developed in order to make quantum computing more accessible to a lot of adapters, a lot of students, a lot of specialists and companies that could work with this type of quantum computing. And it is a kind of AI generated code, and therefore the assistant is powered by IBM Watson and IBM Granite code. So can be explained as follows. Whereas ChatGPT is a more general purpose large language trained model, the IBM based system on Watson and IBM Granite is more specific to programming, to coding in the quantum world. And therefore, that's a nice approach in order to get more programmers, more adapters in the world of quantum computing. So the tools section is very elaborated, I would say. Here you can find out a lot of information on what circuits are available. There is a circuits library, some packages The standard gates you already are familiar with or will be familiar during the lecture, and the code assistant, so you can get a lot of additional information on how to build up these circuits and these fractional gates that are available here in quantum computing. Then how to measure the qubit system and how to apply the various operators in that field. Here's some information on the transpiler. It's by intention that it sounds a bit similar to a compiler, but I already explained that a transpiler converts or transforms a software from one language to another language, and it is not directly a compiler, because a compiler would produce machine code for a quantum computer that is always more or less based on the gates and on the circuits. Then debugging, as in every other programming language, you are not from scratch completely without failures in your programming code. Therefore, we need debugging tools, and there are some debugging tools in that field on the gates level, on the circuit levels, where you can find out what are maybe problems or failures in the code. Then the primitives of the software development kit. So primitives are abstractions that we can use in order to develop code. Then we have the different execution modes. As I already said, you can produce a job or a batch program, or can combine various jobs in one session or in various sessions. You can learn more on that in the demo field of execution modes and how to manage their jobs. And here you can find out information on the quantum computer hardware that is based on this cloud-based system, and what are the various processor types. We distinguish between single processors, multiple processors. That is like in the, I would say, in the old-fashioned way of general purpose computing, that we have single, multiple CPU versions, and how to get out information on what specific processor type your code was executed here, or native gates and operations. I like it very much, that environment, that you can get a lot of materials, hands-on materials, in order to make your first steps in the world of quantum computer programming, the basics in math and the basics in architecture. That's the part that we share, Patrick and me, in this course. And the course is intended that you have a kind of self-study workload in this module. And I can recommend that you start with the IBM quantum computing system. But if you want to use Google, if you want to use D-Wave, you're completely free. And we are keen on getting good seminar papers from you with interesting topics. But I think that's one of the aims and the goals of one of the last lectures handled by Patrick. So that's the thing I want to share you. There are some additional informations. I have always updated some slides, but more or less I would recommend that you make as a kind of starting point in the quantum computer ecosystem, because right now in most countries and in most other industry fields, we are right in the beginning of what could we do with quantum computing. So I think the architecture, the technology is in a really good and steady development phase and situation. But the problem is, it is not only optimization problems. We can do simulation, we can do machine learning in theory with quantum computing, but the real world applications are under development, I would say. Maybe you get from the news last week, if I remember correctly, Google reclaimed the quantum supremacy again for their quantum computer. And so please be a bit careful when you read such news or such press news. There are more or less really specific problems and specific problems designed directly for the application on a quantum computer that makes up the quantum computer supremacy over a general or a supercomputer. You always take that message with care and with caution, and I think you are prepared to understand the basic concepts behind quantum computing, and if you want to do the first steps as your own in the world of quantum computer programming. So that's from my side, and Patrick, I now hand over the mic and the camera to you.
Yes, thank you very much for your presentation, Horst. And I don't know if you can keep your camera on or you want to turn it off, your choice, Horst. So Horst just talked more about quantum computers and programming, also building on top of what he said in his previous lecture at the beginning of the term. What you have seen now, or you have some understanding now after this lecture of Horst and the one before, different concrete architectures, and you've seen some examples from Qiskit, for example. Now, if you open our Nextcloud directory, what you will find in there is a Jupyter notebook, which will make you familiar with how Qiskit work. You can run some experiments as a simulation on your local computer, but this course is not just about simulations, but you will eventually be able to run this code also on a real quantum computer. What you need is you need an account with IBM's quantum cloud, and you need to, once you have your account, you will get an API token. So you need to paste it into the code in the Jupyter notebook, and then you can actually run your quantum experiments on a real quantum computer. You're most welcome to make any changes or extension of this Jupyter notebook as you wish to get some more hands-on practice. And this could also be a basis for a possible seminar presentation, because every year we have a few seminar presentations which build on top of a larger experiment or project. And for that, this one here could be a good basis. Now, we will come now to the part on the seminar presentation, and there were a few questions in the chat already. So let's get started. What we've seen in this course is we've made our way starting from the introduction and motivation up to quantum computers and how to program them. We've seen theoretical limitations, algorithms, the different gates, and all the relevant theory we need about systems, quantum theory. In order to describe that, we need complex linear algebra. That's the first part of the course, and we have finished this. Now, in the second part of the course, you will work on a topic of your choice and prepare a seminar presentation, which will take place in January. There are lots of resources where you can find possible topics about seminar presentations. There are numerous applications that you could look into, like quantum machine learning, quantum cryptography, information theory related to quantum computing. And there are lots of possible seminar presentations in our course book that we've been using now throughout the term. take a look into it, and there are lots of possible seminar presentations. We've also talked about this book here, Quantum Computing since Democritus. It's a hard, tough read, but it could also provide you with lots of proposals on possible seminar presentations. You can also do a search on Google or Google Scholar to find more topics and so forth. Quantum machine learning is something that is also super interesting for us. And since I'm a professor of artificial intelligence and many of you study AI here, every year, lots of seminar presentations cover quantum machine learning, for example, because with quantum machine learning, there are lots of different opportunities, like you could train models faster, you could generalize better from less data. All of that is probably super interesting if you're in AI. And there is a very good book on that. It's called Machine Learning with Quantum Computers. It's the second edition. Before, the book was, I think, called slightly different in the first edition, like Supervised Learning with Quantum Computers or something like this. So make sure you pay attention to the second edition of that book. There's also an interesting course on EDX as one example that is called Quantum Machine Learning. A very good course that appeared probably 6 or 7 years ago or something like this. And that one largely addresses the D-wave world, so quantum annealers, which are more of a niche that Horst also talked about. Now, what do we expect regarding your seminar presentation? There are a few slides in the first chapter of this course, and I'll talk about this now. We have finished our lectures up to here. We have finished them a bit earlier because we have also done lectures, for example, on a public holiday and so forth. And we will also have a guest lecture in a few weeks, concretely on December the 6th, where we have a visitor, but I'll announce that in time. So the examination of this course is you will give a seminar presentation on a topic related to quantum computer. Most students that take this course are from some engineering or science discipline, so your talk would typically be something technical like quantum machine learning or encryption or some other quantum algorithms, whatever. We have some students that come from electrical engineering or mechanical engineering. You can think about algorithms, or a few years ago, there was, for example, a mechanical engineering student. He wondered about requirements for manufacturing quantum computers. So you see, there's lots of possible topics. If you come from a more business discipline like business information systems or business, you could also give a seminar presentation on a business-related topic, like maybe challenges in commercializing AI, but your topic should somehow be related to your discipline. So if we have all AI students just giving some marketing presentations, that's not what we would expect from you. And you have plenty of time to prepare your seminar presentations now. Very importantly, groups of students are 3 to 4 students. I already got a few emails with students asking for exceptions. So there are no exceptions. There is not a presentation by a single student. We don't allow groups of 2 students. We don't allow groups of 5 students. So it's 3 to 4 students. And if you still need to find someone for a group, we have a forum in our iLearn course. So there's lots of opportunities to connect to others. And there are lots of resources on the internet, like books, Google Scholar, and so forth. In early December, we need to finalize your seminar topic. So you have some time now to think about a seminar topic, to investigate deeper. And I had also put in a news on iLearn a few days or like 2 weeks ago approximately. So the next steps are, and we can also briefly screen share this so that we are all on the same page. I'll just switch the screen share, which takes a short moment. So I had put this here in iLearn. You need to be thinking now about a group and a topic. Once you have this, you need to submit a few things via this iLearn course. Concretely, if you open this iLearn course, there's at the bottom this presentation thing here. It will open only today as of 5 p.m. and you need to submit until the end of December the 1st. What you need to submit is the names and student IDs of all group members, as well as your topic. One submission per group, so one of you will submit this for all the group members. Don't do multiple submissions. And it's very important that you follow all these deadlines. And I know we have lots of students watching this course on YouTube who were not able to join this course because this course is capped at 120 students. It's very important that only the students who have actually signed up to exactly this iLearn course, so the AIX BM4, only those students can actually do the presentation. So don't try submitting names and students' IDs of students who are not registered for this course because they will be filtered out. So only students who are in this iLearn course can sit the presentation or sit the exam, because that's why we have a cap, because we're just unable to examine 500 students. We wish we could do that, and we're super happy the course is so popular, but there's a reason why we have this cap. So you need to submit this, and again, bear in mind, only students who were able to sign up for this course can take this course for credit. If you submit names of students who didn't sign up, they will be filtered out. And then I see there are lots of questions coming in the chat. I'll look at them in a moment once I have finished my part, because then probably lots of these questions are disappearing. And we will meet on December 6th via this Zoom session. We will meet at 2 p.m. At 2 p.m. we will probably have a guest lecture first, and then we will look into your seminar topics. And you will briefly present your proposal that you had submitted before. Your proposal presentation should only be 1 to 2 minutes, 1 to 2 slides. So just very briefly, which topic you have picked and briefly what you want to do. Some students, they not just give a seminar presentation on some seminar topic, but some students, they write lots of code and do experiments and they present that. We are also fine with this. And then on January 11th and 12th, which is a weekend early next year, there will be these seminar presentations on campus. And we will simply see who presents on January 11th and 12th. It depends on the number of submissions and how many we can finish on January 11th and how many on January 12th. When we do these proposal presentations on December the 6th, we start with group 1, then group 2, group 3, and so forth, because once I have reviewed your submissions, say on December the 2nd, or sometime before December the 6th, I will upload the list of groups in Nextcloud, and I will ping you here in iLearn. So there'll be a list of the groups and their topics, and then the proposal presentations will just start with group 1, group 2, and so forth. All of these deadlines are definite, so you need to submit this by December 11. You need to be there on December 6 in this Zoom call. If you miss any of these deadlines, you won't be able to continue the course, and there will not be any exceptions. So that's very important. And before I look into your questions, I'll continue with my PDF file. So in early December, we will have finalized your seminar topics. And then you will be working on your seminar presentations during the term. We will be available if you have any questions. We can meet on campus or via Zoom whenever you wish to. And when you have your questions, and then in January, we have the seminar presentations. And these seminar presentations take place on campus, and there are no exceptions to present online. In the past, we were happy to offer exceptions, but then suddenly 50 grandmas died. And yeah, we want your grandma to survive this quantum computing course. And we're sure your grandma would survive if there are no exceptions that we offer. When it comes to the marking of this core of your presentations, or we said your presentation should be about 15 minutes. 3 to 4 students will present in total for 15 minutes. There will be a 5-minute Q&A session after your presentation, and you can score, or your group can score up to 50 points, up to 5 points in the beginning for briefly motivating your topic. So why you're presenting this topic and why you think this topic is relevant. Obviously, the main part of your presentation is crucial, in which you may be presenting an algorithm or some experiment or something. This can be up to 20 points. You need to cover any preliminaries you think are important, maybe some maths or some other algorithm or something that we didn't discuss in that course. So just, or if you want to revise something that is super crucial, briefly do so. There will be up to 10 points. Your slides don't need to look super fancy, but it shouldn't be just a white background and black text. So your visualization will also carry up to 5 points. So that's 40 points for the presentation and 10 points for the Q&A. And the score of up to 50 points will be converted to a mark. So 50 points will be a 1.0, which is your final mark. If you have 49 points, this will be a 1.1. But we only have valid marks 1.0, 1.3, and so forth. So if you have, for example, 48 points, it's a 1.2, which is not a valid mark. So we floor this to your advantage. However, if you score 47 points, that's a 1.3, and you need 20 out of 50 points to pass. So this is the marking, and those are the rules. Now we've received lots of questions here in the chat. So the first question already an hour ago was that I talk about what my expectations are. I think I already covered this. And you should start with your seminar topic as soon as possible. So you need to be reviewing papers, you need to find sources, you need to check if you can handle this for January. So start as quickly as possible and submit your topic, because you will need a few weeks to probably find the topic or discuss it with your group. Until December 1 via iLearn, you can submit as of today if you wish. And on December 6, you will just give this proposal presentation. There will not be any mark for the proposal presentation. It's just 1 or 2 minutes, 1 or 2 slides, and we'll give you feedback on your proposal. And sometimes there are like 5 groups that want to do quantum machine learning. If that's the case this year, we will also use that session just to make sure these groups can all distinguish each other, or can distinguish themselves from each other. So we try to find a focus that actually makes sense. You should there's a question here, direct message, if you can take a topic not related to your field. As I said, if you are an AI student and you just do a presentation about marketing of quantum computers, we would be very unhappy to see that. It should be, if you're an engineering or science student, your presentation should be engineering or science. If you study business, probably there's more of a business topic. However, if you're a business student and you want to dive in detail into a quantum algorithm, then that's fine too. And there is a question, if a group of 4 students, where 2 students are from business and 2 from engineering, if they can still do a business-oriented topic, that's fine. I'm okay with that one. So I think I've answered all the questions that were sent here. Lots of them were direct messages, so you didn't see them. There's one student who says he studies applied computer science and wants to do something with quantum computing and medicine. Yes, that's perfectly fine. And you have quite some time now in the next few weeks to think about your seminar presentation, find a group, and in case you have any questions in the next few weeks, just contact ideally directly me, since I'm the main lecturer of this course. And if there's anything uncertain, I would discuss this with Horst Kuhnhardt directly. So, are there any other questions? So it looks like there are no more questions. Then also make sure you understood all the lectures we did so far, which was quite a lot of content in a short amount of time. Make sure to do revisions where necessary. Otherwise, it could be awfully difficult for you to prepare your seminar presentation. All right, then I wish you a good weekend. Take care and bye-bye.